See what I did there? I just solved this for v by subtracting mgr to the other side and then multiplying by 2, dividing by m. Factor out the g. 3.3 minus 1 is 2.3. Good grief. Seriously. Goodness gracious. What is wrong with me? Don't answer that. So you're 2 times 9.8 times 2.3 times 24. I missed 24. 32, come on. 32.9 meters per second. That's the speed it would go through v, through the point C. How do we figure out the radial acceleration then? Yeah.
Something just doesn't make sense to me. I honestly just don't understand where you, because I see that you have, or you got the 9.8, but once that happens, I have no idea where you get that 2.3 and then the 24.
So it wasn't this stuff.
No, it wasn't that. It was
All right.
once you went from there going into substituting the
This is 3.30R. Okay, so if I draw the free body diagram at C, what's going on there? What's at play?
At point C.
Yeah. Right, we got the force of gravity like that. You got what? I think you got normal force like this, don't you? No.
That'll be all the way.
Oh, I'm an idiot. Yeah, I was about to get really, really confused. The normal force the normal force should point that way. Duh. Sorry. Normal force. So normal force like this, mg like that. Anything.
MV squared over R.
That is not a force. But that is an important question. How about the mv squared over r? Well, that's equal to the normal force. The normal force is what's giving it that center-seeking force, right?
Is MV squared over R, that's the acceleration?
That is the, it is mass times the radial acceleration.
So all you do is just do MV squared.
How about the tangential acceleration? Well, the tangential acceleration, m times the tangential acceleration, is equal to mg. Because the tangential acceleration is the part, which is tangential to the motion. So the motion's going like this. So this is the tangential direction. That's the radial direction. mg is directly tangential. So the tangential acceleration is, in fact, g. So that's why the tangential acceleration is 9.8 meters per second squared. As we've mentioned, we'd like to put a 10 there, but On the other hand, the radial acceleration, what's that? That's v squared over r, okay? So you can use this v squared divided by r. That's the radial acceleration. The radial acceleration in this case is actually 45.1 meters per second squared. What's the acceleration then? It's the vector sum of both of these, right? So like this is basically a sub r r hat. Maybe if I put a sub r as positive, then I guess I have to put a minus here. I don't know. And then the tangential goes like this. The actual acceleration is the combination of both of these. This is the acceleration. It's like that. It's neither radial nor tangential. It's the vector sum of both of those. The acceleration here, by the way, would be the square root of ac squared plus ar squared. Sorry, at squared plus ar squared. Whatever that would be, you know? He didn't ask about that, but that would make this problem more awesome if he had. Now, you can disagree with my definition of awesomeness. That's your prerogative. But you'd be wrong. I won't apologize. I learned that from Trump. Let's see here. So anyway, other questions? I think I've talked too long about this already. Yay, the fan is back. Here's one where letting h equal to 0 at the ground would be kind of like stupid. It's a fun one. Teeter-totter. Right? And suppose you've got like that. And you want to come up with the potential energy function for this thing in terms of the angle. What angle would be natural? How about this one? If this angle is theta, what's the potential energy? As function of theta, of course, right? Describe the potential energy as a function of theta here.
It would just be the mass of one times gravity times sine of the angle times the length of the mass.
Yeah, we need the lengths, don't we? Let's say this one's at L1. Let's suppose this one's at L2.
You also have to know the height of the fulcrum, don't you?
Do you?
Well, it depends on where you set 0 to.
Right. What's that?
If you set the height of the potential energy equal to 0 at the fulcrum point, then you'll be fine.
Exactly. So that's what we want to do. We want to make quote unquote h equals to 0 here, right?
Yeah.
Or y equals to 0. So if you do that, then m1 is at y equals to, let's say y equals to 0. That's maybe better. So y equals to L1 sine theta, right? Whereas M2 is where this is also theta, right? We're assuming that it's not bent. It's like a straight teeter-totter. And so,
It would just be negative.
exactly. So you look at these little triangles right here, is what we're looking at, right? So this right here would be L2 sine theta, but of course, as you've mentioned, it's minus because it's down. The net potential energy for a system, if you have more than one body making up a system, in this case the teeter-totter, I'm talking collectively about M1 and M2 as making up this system, right? So the net potential energy is the sum of the potential energy for M1 and for M2. I'm assuming that the board which connects them is essentially massless, and so the energy is totally wrapped up in M1 and M2. And so the potential energy then, U, as a function of theta would be M1 G L1 sine theta minus m2g L2 sine theta. Or if you like, m1g L1 minus L2 times the sine of theta. Assuming there's no friction, right? What's that? Oh, I'm sorry. I just assumed they're equal, didn't I? Doofus. Not you, me. So I guess I can pull a g out. I can pull g sine theta out, but that's it, right?
Are you assuming the lengths are also different?
Yeah, possibly.
The only thing similar is theta. Just because the board doesn't have.
Yes. Sorry, I have to process. Then you could do fun stuff like suppose you give it a tap, and then you can think about how does its speed vary as it moves, energy being conserved, right? You've got a trade-off as M1 is gaining potential energy, M2 is losing it, and vice versa, right? So you get some sort of oscillatory motion, right? What's that? Ah, yes. If we give the board mass, then we can think about the rotational kinetic energy of the board as well, in terms of the moment of inertia and such. But now you're getting ahead of me. That's a little bit later in the course. But this one we can just do with particles, and that'll be enough. One final thought for you guys before we leave. If I think about the pendulum again, like this. If this is L, right? If this is theta, right? What I really have, if you look at it, if I put y equals to 0 up here, it's easier, isn't it? See, because then u is equal to mgl cosine theta. None of that figuring we had to do for the problem with the 45 degrees, right? And, but there's a minus, right? Right? So, excuse me, what's the energy then? Well, I mean, that's the potential energy. If you calculate du d theta, what do you get? That, right?
It's MGL or something like that. Negative.
Well, yeah, the derivative of cosine is minus sine, so minus minus gives me plus. Now, it turns out if you multiply this by L, this gives us the radial component of the force. The radial component force is mgl squared sine theta. And then you could solve this is equal to like, oh, I'm sorry, I'll have to come back to this. I'm going into places I'm not supposed to go with you guys. I'm sorry. Go vote in your primary. Whatever it is you want to do. Go Bernie!